This is the key for homework 2. We're asked to determine the position of equilibrium for these three equilibria and their acid-base reactions. So we want to circle the side that's favored at equilibrium. We want to, of course, evaluate the stability of the two bases. Typically those have anions, and if they do have anions, we can use areo. Using areo in this case, we have atom is the first point of difference. There's an O versus an N. We know that the O provides for a more stable anion, and so that's going to be the side that's favored at equilibrium. Drawing curved arrows for each reaction, typically we'll draw those arrows on the left side, even if we choose the left side to be more stable at equilibrium. That's just sort of by convention. So I'm going to draw those from the left side. Every acid-base type of arrow push, we'll call it a proton transfer, has two arrows. Second question, A, atom, two oxygens. That doesn't help us. R is resonance. The ethoxide here has no resonance, whereas here we have the ability to do the allylic lone pair resonance structure. And so again, this is going to be more stable because the base has some resonance. It's a more stable base. Again, we can draw our arrow push. Typically there will be a OH bond there, and probably should redraw this to show that, but I'm just going to imply that the OH bond goes back onto the oxygen. The last one, we have a C- and a C-, so atom doesn't work. Resonance, there's no resonance for this acetylide anion or this alkylidine anion. The next one is induction. There's no difference in electronegativity in terms of the different groups on these two molecules, so that leaves us with orbital. This is an sp orbital. This is an sp2 orbital, and we know that the negative charge will reside more stably in an sp orbital, and so we circle the left side in this case. If I want to draw, let me put the hydrogen in here so we can draw our acid-base arrows. And it kind of just goes like that. Again, two arrows. One to remove the H with the base, and the other one to show the CH bond moving back and forming this anion. The next question is draw the skeletal structure of this compound. We need an octane. 1, 2, 3, 4, 5, 6, 7, 8. 3-ethyl, 2,2-dimethyl. Looks like that. And then we want two constitutional isomers. So all we have to do is match the number of carbons here. There are no double bonds, there are no rings, and so we know that if we have the same number of carbons, we'll have the same chemical formula, and thus we'll have a constitutional isomer. So how many carbons are there? Well, I drew 8. I drew 8 carbons in my main chain. I added 2 more over here and 2 more over here, so I have 12 total carbons. The easiest structure to draw with 12 carbons is simply a 12-carbon structure. 1, 2, 3, like that, dodecane. That is a structural isomer of the first compound. In order to draw another structural isomer, I could cleave off one of the methyl groups and just put that on an 11-carbon chain in some random location. So let's draw an 11-carbon chain. 1, 2, 3. Let's put the methyl group right here. That's a structural isomer. Let's try that again. Let's put the methyl group right here. I hope you're catching on. All we have to do is move one little piece around. You could have also moved the ethyl group over a couple of bonds. You could have taken one of these methyls and moved it over. Now we could probably draw 50 different constitutional isomers here. I'm going to stop here. I hope you get the picture. Once we've established that there are no alkenes or double bonds, there's no degrees of unsaturation, it's just a matter of rearranging the carbons. Third question, identify the Lewis acid and the Lewis base present. And it didn't ask us for arrows, but we can practice those too. And so the thing we're observing here is that the N is gaining a hydrogen. So we can think of the arrows like this. And that will show us the acid-base reaction that gives us this structure. And so this is the Lewis base. It's acting as a Bronsted base in this case, and the Lewis acid is really just the H+, but we'll call it the water in this case. And the second one involves just one arrow, forming an N aluminum bond. And so the Lewis base, again, is the nitrogen with its lone pair. The Lewis acid is the acceptor of the lone pair, and that's the aluminum. Number 4, we're asked to use areo to identify the most acidic and the least acidic of the bold hydrogens here. And so we have 4 of them. Here we'll underline them in case you didn't find them. And we're asked to use areo to identify them. So let's say, so we just need to identify 2, most and least. And we can probably put them all in order. So let's call most 1, least 4, and we'll put the other ones in order as well, as long as we're working on this exercise. So areo atom, the 2 atoms that will likely have the most acidic hydrogen will be the 2 oxygens that can most easily accommodate a negative charge. How do we decide between the 2 oxygens? Well, this one has resonance ability because it has the double bond. And so this should be number 1. This should be the most acidic. This should be the second most acidic. Then we want to decide between the rest of them. There's an NH and a CH, and again, A tells us that the N should be more acidic than the C. And if you look up the pKa of an NH bond, as we see on table 3.1, it's about 38, and a CH is about 50. So there's a significant difference in acidity, and the pH of the pKa of an OH bond is somewhere around 17, depending on the structure we have around the OH. But 16, 17, 18, those are all fine values for that. And this one is somewhere around 5. So we can see there's a significant difference in acidity for all 4 of these indicated hydrogens. Fifth question asks us to name this alkane. So in this case we need to number the main chain. Probably want to start numbering from this side over here nearest the substituent, so we give that the smallest possible number. So if we number, we end up with 13, I think. And that's try that again, tridecane. So that's the parent name. We've got a 2-methyl, and we've got a 6-methyl, and we have an 11 and another 11 dimethyl. Put those all together, we should write tetramethyl. And we have a 9-isopropyl. This Y shape tells us it's iso. And we have a 6-propyl. It is not iso, it's just propyl because it has the straight chain. So now we need to put all these together, I and P and M. So I comes first, so let's try to write this as best we can. Dashes between letters and numbers. Then comes tetramethyl with all its numbers, so 2, 6, 11, 11, tetramethyl, dash 6, propyl, and then we don't put a space here, we start writing tridecane. So a nice long name, we had to put it on 2 lines, no big deal if you had to do 2 lines. So here we want both chair structures. So let's start by drawing our favorite chair. And then we want to put the substituents on, and we want to start some random numbering scheme. Again, it doesn't matter what direction you choose or what numbering scheme you choose, or even if you use numbers according to IUPAC rules or whatever. We just use these numbers to figure out where to put substituents. So I'm going to start my numbering like this. You may have started it slightly differently. Doesn't matter as long as we're consistent. So now I have a down methyl on the carbon number 1, so that would be straight down as axial. Skip carbon 2. On carbon 3 I have an up ethyl. Up on carbon 3 is a equatorial. I'm going to put the ethyl down here. And then number 4, we have an up T-butyl. 4 is an upward facing carbon, so we would draw a T-butyl. Now I want to do a ring flip, and let's draw the opposite ring now. And we'll put our numbers on these carbons again. Now carbon number 1 went from down to up, so this is now carbon number 1. And let's put our substituents on there. So on carbon 1 I have a downward facing methyl group. Now it's down and equatorial. Carbon 2 has nothing. 3 has an upward-facing ethyl group. And carbon 4 also has an upward-facing T-butyl group, although upward now is equatorial. And then we were told to add all hydrogens for the ring. We don't care about the hydrogens on the substituents, but if you drew those, that's fine. And so this is just practice drawing the proper orientation for axial and equatorial type substituents. Make sure that all your equatorial bonds parallel a set of bonds that are in the ring. And all your axial bonds are either straight up or straight down. So all these equatorial bonds should be parallel to a set of CC bonds that's in the ring. And all my axial are straight down or straight up. Circle the most stable chair. So the most stable chair will have the largest group in a equatorial position. And so this T-butyl is axial right there. Now it's equatorial, so this will be the most stable chair. It has T-butyl and methyl, both equatorial, and only the ethyl in the axial position. Alright, question 7. Conduct a conformational analysis of the following molecule by rotating around one of the bonds here, like that. So we want to start with the first structure. We're going to have, remember that we sort of have a top and a bottom to this arrow. And now the arrow is going to be our sight line as we look into the page. Above the arrow, above this dot, is a methyl. And then we have the two hydrogens that are not drawn in. And then, of course, we have the back carbon as this circle. Above the arrow on the back carbon is the ethyl. So here I have an ethyl. Then I have the methyl right here. And I have another hydrogen going down into the left. So now this is eclipsed. And in fact, this is the highest energy conformer. How do we know that? Well, the ethyl is the largest group on the rear carbon, and the methyl is the largest group on the front carbon. And so we already have those eclipsed, so we know that we're already at the highest energy conformer. So let's draw the other 5 conformers. So we're going to rotate 60 degrees, and I'm going to keep the front carbon the same for all of these rotations. So I can go ahead and just redraw that automatically, like that. I'm going to rotate 60 degrees, and so we're going to rotate, let's do a clockwise rotation. So now the ethyl comes out like that, then the methyl, and then the hydrogen here. And then I'm going to rotate again 60 degrees to come up with another eclipsed conformation. And now the ethyl is going to be basically eclipsed with that hydrogen. The methyl will be eclipsed with the other hydrogen. And up here we have a hydrogen that's eclipsed with the, sorry, that's not an ethyl up there. This is just a methyl here. So I have a number of eclipsing interactions. I'm going to try this again. 60 degrees again, keeping the front carbon the same. Now we're on to a staggered conformation. The ethyl goes straight down. Then the methyl is up and to the left. That's pretty long. Let's try to fix that a little bit. And lastly, the hydrogen is up and to the right. Another 60-degree rotation gives us the final eclipsed conformation. And here the ethyl is eclipsing with the hydrogen, the 2 methyls are eclipsing, and 2 of the hydrogens are eclipsing. And then I think we need one more. And again, front carbon is the same. And now the ethyl is out and up and to the left, the methyl up and to the right, and the hydrogen is down. So we found the highest energy by looking at the 2 largest groups and putting them eclipsing of each other. So the lowest energy then should be 180-degree difference from this molecule. So 1 60-degree rotation, 2 60, 3 60s. This is where the 2 largest groups are as far apart as they can get from each other. And yes, there is this methyl-methyl gauche here. There's nothing we can do about that. We just want to prevent the ethyl and methyl gauche. So we want to prevent this sort of interaction. That's worse than this interaction here. So this would be the lowest energy conformer. And we know that it's a candidate to be lowest because it's one of the staggered conformations, and it has the minimum amount of gauche interactions as one of the staggered conformations.